Hey folks, we are continuing with our particle motion notes. So there is perhaps no more important, if not fun, type of rate of change, and that is of motion. Actually, this is why Newton invented calculus to begin with. So there's a classic legendary story about a mathematician named Zeno. And Zeno posed this question to his students, and his colleagues, how is any motion possible? How is movement possible? So if you stood 10 feet from the door and you wanted to walk out a door, you'd have to first get to 5 feet away from the door. Then you'd have to get 2.5 feet away from the door. And then you'd have to cover 1.25 feet away from the door, and so on and so on and so on. How many halfways are there between you and the door? Well, there's infinitely many, right? So you can get halfway there, and then there's another halfway, and then a halfway, and then by the end, you're taking like these super baby tiny steps, but you still have to cover that distance. Well, Newton solved this problem, and that was a problem for a long time, is how do we handle infinitely many things? And so mathematicians for a long time just kind of turned their head and pretended like it never, well, we just kind of ignore it. Well, Newton and Leibniz come along, and Newton kind of did it first, I think, but so that's called Zeno's paradox. Zeno's paradox is, how is any motion possible? So Newton comes along and he says, well, what we can do is we can find this thing called the limit, and the limit allows us to handle things infinitely many or infinitely small things. And so it kind of solved the problem that Zeno had. Anyway, okay, so I'm getting off the trolley here. What we're talking about is we're talking about particle motion. We're talking about a particle that moves in one dimension. So this isn't projectile motion. Those of you in physics maybe have done some projectile motion stuff. Like a cannonball gets launched from a ship and it tries to attack another ship. That's a projectile. Baseball gets thrown in the air. That's a projectile. What we're talking about is a particle. So I'm going to show you some, and there's three things that we're going to talk about when it comes to that particle. We're going to talk about the position of the particle. They usually use the letter S or X or P. Most of the time it's S or X, but sometimes it is P for position. But that stands for where the particle actually is. Then we also talk about the velocity of that particle, and we talk about the acceleration of that particle. So let me start off by reviewing an earlier thing that we did when it comes to graphs and what they really mean. So some kids, especially, or myself even, when I would have looked at this, and even in high school, I look at this, I would have said, okay, guy went up a hill, then he went down a hill, then he went up a hill, and then he walked across the top of the hill. That's not at all what this picture is. We have no idea if there are hills. There might be hills, but we have no idea if there are. So let's read a little bit more here. Every morning, Tom walks along a straight road from his home to a bus stop, a distance of 160 meters. The graph shows his journey on one particular day. So this is the time, all right, that makes sense. This represents how far he is away from home. So as this goes up, it's not him climbing a hill, it's him going away from home. So if we were to look at this, what's happening in this story, for the first 50 seconds of Tom leaving his house, all this indicates is that he's walking away from home. He gets 100 meters away from home. Then what happens? He doesn't go down a hill now. What happens is what's happening is the distance away from home is getting closer, is getting smaller, I should say. So what he did here, something happened. He must have forgot something, and he returns home. He starts heading towards home. Like, let's say he can't find his cell phone. Well, he's walking, and then he sees on his ground, he sees the cell phone here, and he picks it up, and then he starts walking back to the bus stop. This doesn't mean he's walking up a hill. What does this then represent? Well, this is him actually getting to the bus stop. Remember, 160 meters is where the bus stop is. So he gets to the bus stop, and what happens? He just stands there. So time is still passing, but his distance away from home is not changing. So just remember that when we're looking at a graph, up doesn't always mean up on the graph. Up could mean different things depending on what our graph is labeled as. So as we look at these two pictures, here we go, distance from home again, time. He didn't climb a mountain and then walk across the top of the mountain and then slide down the other side. No, this means he walked away from home. What happened here? At some distance away from home, whatever this distance is, he stopped and he just stood there. Wherever there is, he stopped, and then he came back home. So my guess is if we're doing our bus stop example again, he was late for the bus. See how this is steeper? So he kind of ran for the bus. Then he waited for the bus, but it never came, so he knew he must have missed it. And then he decided to walk a lot slower back home. He didn't have to rush to get back home so he could get a ride to school. Okay, so think for a second, pause here, and try to describe what do you think is happening in this scenario. Okay, let's see how you did. So in this case, Tom realizes that he's late for the bus, so he starts running. Tom is like me, though. He's out of shape. And so as he's running, he's slowly slowing down. He's not running as fast. He starts off almost sprinting, and then by the time he gets to the bus stop, he's so tired that he's basically barely running at all, and he finally gets to the bus stop and stops there. Okay, so this isn't a real steep mountain, and this isn't a curvy mountain. These are distances from home. So coming back to this, I want to look now at, I think this sort of does a nice job of demonstrating what I'm talking about here. So S of t, this is our position function. This is our particle. The position of the particle is based on t cubed minus 6t squared plus 8t. But that's the motion of the particle on a straight line. So what happens is, this doesn't mean the particle goes up and then goes down and then goes up. This represents how the particle moves along that straight line. Now notice a couple of things here. We start at the beginning. Then, let's go up to this peak here. How high is that? What's that y value? I would say at about 1, or here we can see the time right there, at about 0.84, about 1. The graph should be at a height of 3. No, what that means is that it's in a position, it's moved 3 units to the right. Then the position starts to go, oops, keep grabbing the wrong thing. Now the position goes down, but that doesn't mean down, it means backwards. And then it starts going up again. A couple things I want to point out, and this will make more sense the more examples we do. What do you notice about the slope of the graph here? All these slopes, if I had you draw a bunch of different tangent lines here, all those slopes would be positive. Which way is the particle moving? To the right. So I'm going to highlight this again. The particle moves to the right. Then, what are these slopes after this peak? If you did the tangent line, all of these slopes would be negative. What's happening to the particle when all those slopes are negative? It's moving to the left. And then here again, what are the slopes? Slopes are positive, and it's moving to the right again. Couple of things to point out. What's happening at exactly 1 second, let's say. What is the slope at this spot? The slope is 0. If I drew a tangent line here, it'd be horizontal, which means that the motion stops. So it doesn't really stop. I think I'd have to talk to Roop again about that. But somewhere in between here, right at that moment, look what happens. Our graph, our particle, stops going to the right and starts going to the left. You see how that changes? That's what we're looking for. And the reason that occurred is because what is the slope of the tangent line here? Positive. That means the velocity is positive, which means the particle's going to the right. The particle's going to the right. Then, what's the slope of the tangent line? So the slope of, maybe I should have said this earlier, darn it. I wish I would have. Let me show you this. I probably should have written this earlier. We have, is there a good place for this? I guess I'll just squeeze it at the top here. We have S of t. I want to write all three, but I don't think I'm going to be able to make it. S of t is equal to position. S prime of t is equal to V of t, which is equal to velocity. And then S double prime, and that's what this is down here, S double prime of t is equal to the derivative of velocity, which is equal to A of t, which is acceleration. So velocity is the derivative of position. So if I go back to my picture here, and we look at this, if you look at the derivative of position, that's all the slopes. When the slope is positive, my particle moves to the right. When my slope is 0, my particle stops. When my slope is negative, my particle moves to the left, to the left, to the left. Negative slope, negative slope, negative slope. Now I get here. What's my slope again? My slope is 0, so my particle stops. On the other side, my particle is positive, so now we're moving back to the right. So this is a visualization, I hope that helps in terms of understanding what we're talking about when we're talking about particle motion. This is the graph of the position of the particle. It doesn't mean the graph goes up, down, and up. It doesn't mean that, okay? This is the position function. It tells you how far the actual location at this spot here at around 3 seconds, I got a y value of -3. That means that it's at a distance of -3 away from 0. Okay, there's a couple of things that I want to point out too, and I think this does a nice job of showing it. So here's our particle. I got to get it so we can see like the 20s, maybe even the 30s. Okay, a couple of things. So here's our function. This is our particle, our function particle. Our position, let me try again. This is our position. This is our velocity. This is our acceleration. So if you look at these values, I think this is kind of interesting. So at time 0, the particle is at a position of 0. Its velocity is -12, which means it's already moving. When we decided to start the watch, our particle was already moving. Now, because the velocity is negative, watch what's going to happen. As soon as I move in time, this particle should move to the left. Because my velocity is negative means it's headed in the negative direction. Boom, there it goes. So my particle is moving to the left. I don't know if I don't like those. Let me turn those off. Then my particle is still moving. Look at my velocity is still negative, but look at what's happening to the number. That number is getting bigger, technically. It's getting closer to 0. And then the particle becomes somewhere in here. I'm not going to be able to get it exact, probably around 2 seconds. The particle then changes to having a positive velocity. So now what's going to happen to the particle? It's going to start moving to the right. The particle is moving to the right, and it moves right for the rest of the story. So when I go back to time 0, my velocity is negative. So my particle is going to move to the left. As soon as my velocity gets 0, boom, it stops. Oh, I nailed it. My particle is now, look at my velocity. My velocity is 0. That means that my particle is not moving at all. My position is -20, so I'm 20 units away in the negative backwards direction from 0. But I'm accelerating positively. So now I'm going to start getting pulled towards the positive side, which means I'm going to get pulled this way, and now all my velocities are positive. So let's talk about the particle speeding up and slowing down. Notice my velocity is negative and my acceleration is negative. This means that my particle is moving to the left and it's getting pulled to the left. So it's accelerating in the same direction that it's moving. That means that my particle is speeding up. My particle is speeding up. My particle is speeding up. That's because my acceleration and my velocity have the same values. Then somewhere in here, maybe around 0.5, my There it is. Look at my acceleration is 0. My particle stops accelerating. This is when you hit cruise control on your car. You're still going a velocity. You're not speeding up though, nor are you slowing down. I'm still moving left because I have a negative velocity, but my acceleration is 0. But watch what happens now. Now my acceleration is positive. So what's happening is I'm moving left, but my acceleration is pulling me to the right. That means that this particle is slowing down. So you'll see this velocity number getting pulled closer to 0 until that acceleration keeps pulling it until it actually gets down to a velocity of 0, somewhere in there, if I can get it. Let's see. Oh, I had it. There we go. Now my acceleration is positive. My particle isn't moving technically for that 1 millisecond at 2 seconds. And then it starts, the accelerating is positive. Now my particle is speeding up here. Watch how much faster it goes over time. That's because my particle and my particle's velocity and acceleration are the same value. So my velocity is going to the right and my acceleration is pulling it to the right. So right now my particle is increasing in speed. It's speeding up. Now let me go back to the beginning. As soon as we start our clock and we start measuring this after 0 seconds, my particle is going to be speeding up because it's going to be going to the left and it's going to be getting pulled to the left. It's getting accelerated to the left. So right here, my particle is speeding up. Now you can't really tell because the window that I picked wasn't a great window, but somewhere in here, that switch is at 0.5 and then they change around. This is the last moment. So I'm headed to the left, but I'm not getting pulled in either direction. So I'm just going to keep going to the left. But now my acceleration this is kind of like when you guys have all taken driver's training at this point, I think. If you're going 80 miles per hour on the highway and you slam on your brakes, you're still going to go forward for a long time. It's actually crazy how far. You should look it up. It's like 100 feet. So if you're going 80 miles per hour, and you slam on the brakes, your acceleration is negative. You're getting pulled backwards, but your velocity is still pulling you forward. Okay, so maybe I'm over-explaining this. I hope it's making sense. But I'm going to come back to these topics in a minute, and I want you to understand where they come from, that it's not just magic. So if my velocity and acceleration have the same signs, and that's very confusing because kids think if my acceleration is negative, then I'm slowing down. That's not necessarily true. If your velocity is negative and your acceleration is negative, then you're slowing down. All right. So my goal is to get through this chart and then maybe do one example. We'll see how much time we have here. I wish I would have started my clock on when I started this video, but such is life. C'est la vie. Okay, so we've got this idea of what these functions stand for. Now we got some new words. Our first word is displacement. Displacement. This is how far from beginning to end you've moved. So if I go up here, if I go back to my picture, displacement is represented by, so from 0 seconds until basically 3.3 seconds, you have moved 0. You have had a displacement of 0. Because at 0, you were at 0, and at 3.3, you're also at 0. You see what I mean by displacement? Displacement is how much you have actually traveled. One of my favorite football players, actually my favorite football player, Barry Sanders, he used to lose all sorts of yards, and then he would gain them back. And so he'd get hit in the backfield 5 yards behind the line of scrimmage, but he'd break that tackle and then run for 15 yards. Well, his displacement was 10 yards. So we have this phrase distance and displacement. Displacement is strictly take the end position, subtract the beginning position. Where'd you end? Where'd you start? That's displacement. Now, distance traveled is a little bit more complicated. Distance traveled, I'll highlight that in a different color. Yeah. Distance traveled is more complicated. When we get to an example, I'll show you what that means. But that's if I go back to the Barry Sanders scenario, he ran backwards 5 yards and then he ran forward 15 yards. Well, he ran a total of 20 yards then. He went back 5 and then forward 15. He covered 20 yards. That's the distance traveled. His displacement, though, would be 0 or would be 10. So this particle, again, at 0, it goes from here back to negative 20 and then back to 0. Its displacement, there it is. No, about 3.3. Anyway, its displacement is 0. Its distance traveled is 40 because it went 20 this direction and it went 20 in this direction. So hopefully that makes sense, the difference between the two. I'll probably bounce back and forth quite a bit between these. Average velocity. So this should be old news. We already know average velocity, average anything is an AROC. It's the slope formula. So I would take how far I traveled, divided by how much time went over. That's my average velocity. Then when we just say the word velocity, velocity at a time is an IROC. Now, they don't have to say instantaneous. Remember, but when you see just any sort of rate of change, usually it means instantaneous. And we find that by doing the derivative. So if I want to figure out my velocity, I would take the derivative of position. That would give me the slope of the tangent line. Okay, now we're going to talk about something called speed. Speed is something that we most often talk about. How fast were you going? That was your speed. So if you are driving forward at 30 miles per hour and you hit a wall, or if you got your car in reverse and you're driving backwards at 40 miles per hour and you hit a wall, I don't know what I said. Did I say 4? If I'm going forward at 30 and I hit a wall, and I go backwards at 30 and I hit a wall, I hit the wall at the same speed. It doesn't matter which way I'm going. So when we talk about speed, speed is the absolute value of velocity. It's the absolute value of the derivative of position. So speed is, I don't know if I want to highlight everything in here. It kind of defeats the purpose of highlighting, but speed is the absolute value of velocity. Velocity has direction. If you're going negative 30 miles per hour, it means you're going backwards or down 30 miles per hour, but your speed would be 30. Okay, now this is where it gets kind of confusing. When is my particle increasing? When is my particle, the speed, sorry, let me try again. When is the speed increasing? My speed is increasing if velocity and acceleration have same signs. So if I am going to the right, my velocity is positive. And at the same time, my acceleration is positive. That means I'm going to the right and I'm getting pulled to the right, then my speed is increasing. Or if my velocity is negative, which means I'm getting pulled to the left, I'm going to actually write that. I like that. This means I'm going to the right, moving right, and pulled right. This means I'm moving left and I'm getting pulled left. Then my speed is increasing. So you could probably figure out pretty quickly, when is my speed decreasing? My speed is decreasing if, what would be a good color here? I need more colors. Okay, we'll go with this. My speed is decreasing if my velocity is positive and my acceleration is negative. So in other words, I'm going to put that underneath here. Velocity and acceleration have different signs. So if my velocity is positive, I'm moving to the right. But if my acceleration is negative, I'm getting pulled to the left. So if I'm moving right but getting pulled left, I'm going to slow down. If my velocity is negative and my acceleration is positive, that means I'm moving to the left, but I'm getting pulled to the right. I'm going to be slowing down. I'm going to be slowing down because I'm moving left, but I'm getting dragged to the right. At time equals c, if, yeah, I mean, that's kind of obvious, right? Why is this true? I hope this makes sense considering velocity, acceleration is equal to the derivative of velocity, which is the rate of change of velocity. So hopefully that makes sense, right? I mean, if my acceleration is positive, then my velocity has to be getting bigger. Now, if I'm going to the left and my velocity is getting bigger, that means I'm slowing down because my velocity is negative. But if my velocity is increasing, I'm slowing down because I'm getting pulled in the other direction. Times c, position is increasing. So velocity, I don't know why this isn't higher. It seems like this should be higher. If velocity is positive, position is increasing, right or up. If velocity is negative, position is decreasing, and we're moving left or down. So this is worth memorizing. All of these things are worth memorizing. They're something. It's a huge part of the class. So I can guarantee there'd be at least, I don't know, 3 to half a dozen questions on the AP test. For me, a whole test is based on this particle motion. Direction changes when velocity changes from either positive to negative or negative to positive. That's worth noting. So I'm going to change direction. Direction changes when velocity changes. I always like to just say sign. Changes positive to negative or negative to positive. So I hope that makes sense based on what we've talked about up to this point. So if my velocity is positive, that means I'm moving to the left. And then all of a sudden I switch to let me try again. If my velocity is positive, I'm moving to the right. And all of a sudden my velocity becomes negative, that means I'm moving to the left. What had to have happened? I had to have changed direction. If my velocity is negative, I'm moving to the left, and then suddenly it becomes positive, that means I'm moving to the right. So I change directions at those moments. Now, what's interesting is, I'm just going to underline these. I don't think it's worth highlighting. But velocity need not pass through zero to have this happen, or even have a point. So what's weird is it's not a very good physical example, but you could have, like if you're in your car, you can't go forward at 80 miles per hour and then suddenly go 30 miles per hour in the other direction. That's impossible. But these particles are allowed to do that. I don't know the physics of it, but it is legal. So you don't even have to, stop to change directions when you're these magical particles. So basically this section, particles change direction when velocity switches signs. Particles change direction when velocity switches sign. Okay, so I think we could probably muscle through some of the next example, but I think I'm going to stop instead and give you and finish the whole thing in one video.